Hello. My name is Carson. This is Arabella. This is Trevor. This is Heaven. And that is Ella. We did impulse and momentum change.
Okay, so I'm gonna first just explain some of the basics of what impulse and momentum are. So impulse is annotated as a J, and it's equal to the force times the change in time. And then we have momentum, which we write as P is equal to mass times change in, or just velocity. So the objective of this lab is to show that impulse is going to be equal to change in momentum. And it kind of looks like these are different equations right now, but if we unpack this a little bit, we know from Newton's second law that force is equal to mass times acceleration. And then we should know that acceleration is going to be change in velocity over change in time, right? So if we just move time, multiply it by both sides, we get force times change in time is equal to mass, and remember we multiply both times. So it's equal to mass times change in velocity. And does that look familiar? Yes, because we have change in momentum is equal to mass times change in velocity, which is exactly what we see right here. And then what's this side of the equation? That is our impulse. So basically in this lab, we're showing this process. And something I want to show you before we go to the momentum slide is this really cool graph that I worked really hard on. So what you can do is you can say like wow or ooh and ah when the graph starts moving. And H here, so it's on Desmos, H, that's going to be equal to your force, right? And then your time, T of O, that's going to be your time in seconds. And then W, that's going to be equal to the change in time. So we have your final time minus your initial time. Now watch what happens. When you change the force, ooh. And what happens when you change the time? Wow! So we can see here that impulse is equal to the area in a force versus time graph. Wow! So that's kind of what we're showing in this lab. But what is momentum? So I have this friend named Trevor, and Trevor has mass and he has velocity when he's walking forward, but now he has a different velocity. Ooh! So we're changing our velocity, but Trevor's mass didn't change. So what do we have now? We have a change in momentum. Okay, so throughout this lab, we're going to learn how your change in momentum is equal to that impulse, which if we remember is that area under the curve. And yeah, we're going to go text about it.
It's also important to recognize that both impulse and momentum are vector quantities, which means that they consider magnitude and the direction. That momentum is going to be dependent on the direction of velocity, while impulse is going to be dependent on the direction of the force.
Okay, now to be able to make this experiment happen, we have a few materials here. First off, we use our Pascal interface, connected with our capstone, and that's what we have here. As you guys can see clearly, we have our graphs here, measuring force and time. We have our frictionless cart right here. We before calibrated our force sensor with a pulley system and a few masses that we knew. In order to measure velocity, we used a motion sensor right here at the end of the track. And finally, a few weights as well as string to be able to make this happen. Did all our graphical analysis in Excel. Yes.
So with these materials, we can get into our various activities. And so the purpose of activity 1 was really just to set up our apparatus and our equipment. We also measured the cart and we calibrated the force sensor. When calibrating it, you have to make sure to calibrate it horizontally though, because for this lab, the force sensor will be horizontal. With activity 2, once you set up your capstone with your different measurements of the force, and the
Motion
motion sensor. Now what we do is we're collecting our data. So I'll come around here and we can hit record with the card around here. And now we were able to send the cart with an initial momentum and then experience the change in momentum and went back here. And on our graphs, we can look and find the area beneath the force versus time graph to calculate impulse. And we can also go onto our motion sensor graph, and that can give us an initial velocity going this way and a final velocity going this way. And using the mass of the cart with our various weights for different trials, we're able to calculate the different momentums and therefore calculate the change in momentum. For activity 3, really all we did in activity 3 was we were graphing the change in momentum versus our impulse measured by our different things with our apparatus. And that way we were able to look at the relationship between impulse and momentum change to show that they were the same.
So if you notice that we were looking at the area on the curve kind of the same way I showed you on Desmos in this experiment, and then in this example, the cart is going to be Trevor. So we did the same exact thing, just like with Trevor acting as the cart, where I pulled that rope and that's changing his momentum.
And for the method of this lab, we used graphical analysis in order to analyze the relationship we experimentally determined between momentum change and impulse, using the equations that Ella explained to us in the theory.
Okay, so I'm going to go over the results of this lab. So as you can see here, kind of right behind Trevor, there's the change in momentum and the impulse, and they're roughly about equal. You can see in each trial just from the raw data. And then if you look at the graph for an even further clarification of this data, you can see that we used linear graphical analysis, and the equation was y equals 1.2932x minus 0.0564, and we had an r-squared value of 0.9925. So that was really close to 1, which means there's a very strong linear correlation. And that gave us a percentage error of 23.92%. And that percentage error was most likely due to things like friction between the track and the cart, maybe some errors in the calibration, and maybe even some differentials in the graphical analysis. But overall, it was very successful, and we had a really good R-squared value. And it further proved the theorem, the impulse momentum theorem, which states that change in impulse is equal to momentum.
Many of you may be wondering, how is this helpful to me? Well, this can be useful to all of us by MIPS helmet technology. By understanding the principles in today's lab, helmet designers have applied these same rules into developing a low friction internal layer that is built within helmets. Now what this does is it increases the time that the change in momentum happens, which will decrease the force. This is very helpful for concussion prevention because it controls the rotational motion.